Inside a modern enterprise network, a data breach looks like a sudden, chaotic flash flood. Systems are locked, alarms trigger, and data vanishes in seconds. Because of how fast these strikes happen, there is a pervasive assumption in the industry. The saying goes that defense is a losing battle because defenders must be perfect everywhere, but attackers only need to be right once. Before we test that assumption, we need to define the actors testing the network. The most recognizable is the black hat hacker. These individuals breach systems illegally to steal data, demand ransom, or cause disruption for pure financial gain. Sitting adjacent to them is the gray hat. They will actively probe a network without permission, but they typically lack malicious intent. They operate in a legally ambiguous zone, often reporting the flaws they find rather than exploiting them. Then there is the white hat, or ethical hacker. This is a security professional who operates entirely within the law. They work under strict, signed authorization to intentionally break into an organization's systems, finding the fatal flaws before a malicious actor can. Regardless of legal standing or intent, all three actors navigate the exact same system architecture. They hunt for vulnerabilities using the exact same technical toolsets. Whether a basic automated script or a nation-state operation, every single cyber attack is ultimately trying to shatter one of three core pillars. We model targets using the CIA triad. The triangle represents a perfectly stable system. Confidentiality keeps information secret through strict access controls. Integrity guarantees data is not tampered with using cryptographic hashing. Availability ensures systems remain accessible when needed, relying on network protections. Every consequence of an attack maps directly to this triad. Stealing a database destroys confidentiality. Quietly altering a financial ledger breaks integrity. Overwhelming a server with a DDoS attack eliminates availability. To the victim, the loss of any of these pillars feels instantaneous. In reality, the moment of impact is simply the final result of a long, deliberately sequenced chain of hidden events. A cyber attack is a strict sequential dependency graph. You cannot skip steps. You cannot execute the end without completing the beginning. The framework for understanding this sequence comes from the aerospace and defense sector. Lockheed Martin developed it specifically to conceptualize and dismantle the life cycle of modern digital threats. This diagram outlines their model, the 7-stage cyber kill chain. It begins with Stage 1, reconnaissance. An attacker systematically maps the target from the outside. They scrape public records for employee names, identify exposed software services, and reverse engineer the target's technology stack. With that intelligence gathered, they move to Stage 2, weaponization. The attacker builds a malicious payload, like wrapping exploit code into a seemingly normal PDF, designed specifically to trigger the exact weaknesses they just mapped. Notice the dependency here. The most sophisticated weaponized payload is entirely useless without precise reconnaissance to ensure it will execute against the target's unique operating system. Strategically, these first two stages happen entirely in the dark. The attacker is building the weapon on their own hardware. At this point, the target organization hasn't even been touched. Eventually, the attacker has to leave the safety of their own environment. They must push their weaponized payload across the organization's defensive perimeter. This is Stage 3, delivery. The transmission vector could be a highly targeted phishing email, a spoofed malicious link, or a physical infected USB drive dropped in a parking lot. Once the payload arrives, we hit Stage 4, exploitation. This is the exact trigger moment where the payload activates to secure a foothold. Exploitation takes two main forms. It is either a mathematical trigger, like overflowing a buffer in an outdated piece of software, or a psychological trigger, like convincing a panicked employee to click an urgent invoice. The moment that trigger is finally pulled, the transition is practically instantaneous, and the entire system is completely compromised. Delivery and exploitation serve as severe bottlenecks. A flawlessly engineered weapon poses zero threat if the firewall blocks its delivery or if the employee refuses to click the link. Gaining a single foothold is dangerous for the attacker. If the IT department reboots the compromised server, that foothold is wiped out and the attacker is back to zero. To survive a reboot, they execute Stage 5, installation. The attacker embeds persistent access, dropping a hidden backdoor or burying malware deep in the system files so they can return whenever they want. With persistence established, the compromised machine executes stage 6, command and control. It reaches outward, sending an automated signal back through the firewall to the attacker's servers, establishing a direct remote steering connection. This outbound connection is a vital lifeline. It transforms what was initially a blind, automated breach into an actively piloted operation inside the target network. Now, with total control, the attacker executes stage 7, actions on objectives. This brings us right back to our starting point. This final stage is where the attacker actually shatters the CIA triad. The proprietary data is exfiltrated, the databases are quietly manipulated, or ransomware locks every file. By the time an organization's monitors flash red and they realize their data is encrypted, the fight is largely over. The attacker has already successfully completed 6 invisible stages. We can now return to that original industry assumption, the idea that defenders must be perfect everywhere, while attackers only need to be right once. The kill chain proves that quote is entirely backwards. Because this process is a strict sequential dependency, the attacker actually has to execute flawlessly 7 consecutive times in a row. The defender holds a massive asymmetric advantage. To collapse the entire operation, the defender only needs to break a single link. If you intercept the payload during delivery, the exploitation cannot trigger, the installation cannot happen, the entire downstream sequence dies instantly. The specific location of the break doesn't matter. Training a user to delete a phishing email at stage 3 stops the attack, but configuring a firewall rule to block outbound command and control traffic at stage 6 is exactly as effective at preventing the final data theft. This structural reality dictates the daily work of an ethical hacker. A white hat systematically stress tests every link in this chain to identify exactly where the sequence is most vulnerable. They deliver harmless payloads, they test outbound signals, and they map out precisely where an organization can place a block to sever the chain months before a black hat ever targets them. In the end, cybersecurity is a highly engineered discipline. By mapping out the rigid dependencies an attacker relies on, defenders are able to turn the attacker's own complexity against them.